Welcome to the IEEA 2022 Virtual Conference, Malaysia. This is Zubair Hassan Khalid from the Department of Electrical and Electronic Engineering, University of Liberal Arts, Bangladesh, on behalf of the other authors. Today I am here to present our conference paper titled Study of 3nm Cylindrical Gate-all-around FETs with Variations in High-K Dielectric Gate-oxide Materials. Moving on. This is the presentation layout. Firstly, the introduction will be discussed. Then the reason for choosing 3nm cylindrical GAAFET will be discussed. After that, some related works will be shown. Then the importance of the work will be discussed. After that, the methodology, how it is done, will be told briefly. Then we will move towards the simulation results and discussion. After that, the discussions will be concluded. Moving on. This is the introduction. You can see the reduction of the size of memories and other devices are now an increasing demand. So the basic units need to be reduced. Cylindrical gate-all-around FET with a shorter channel length is a candidate of choice to meet this demand, as this transistor can be used below 7nm of channel length. Cylindrical gate-all-around FET shows attractive characteristics and are potential candidates for memory applications and others. High-K dielectrics are a choice to overcome the short channel effects. Transistors consisting of high-K dielectrics show superior features we will show in the simulation part. Moving on. Why 3nm cylindrical GAAFET is chosen? You can see in this picture, the square-shaped GAAFET has corner effects. On the other hand, the cylindrical shaped GAAFET has no corner effects. So advantages of cylindrical GAAFET has no corner effects. It has better electrostatic control. It has less short channel effects. By 3nm, you can see size of the devices are getting reduced. So this is one of the reasons. Another reason is that the Moore's law will sustain with keeping the channel length shorter. Shorter channel length, 3nm is fast and efficient than the bigger channel lengths, and it is trending. We know that Samsung is heading towards the 3nm technology this year. Moving on. So these are some related works with us. In the first paper, you can see they observe the effects of physical parameters for GAAFET. They compared the output characteristics and performance of the design device. They used analytical modeling with Poisson's equations here. In the second paper, they simulated FinFETs with hafnium oxide, silicon dioxide, and air. They observed the performance parameters. They used Silvaco TCAT to simulate. In the third paper, they showed GAAFET better over FinFET in the basis of gate controllability, DIBL, and subthreshold swing. In the last paper, you can see single and double gate GAAFET are compared. They used visual TCAT tool to simulate the device, and they got hafnium oxide effective. Moving on. So this is the importance of our work. If I read from here, you can see in the previous comparison works, different gate-all-around FET having consisting different materials, device structures are simulated and compared. GAAFET is nowadays one of the promising candidates for memory and amplifier applications. The gate-oxide materials keep significant effect on the device performance. No significant works have been carried out regarding the effects of the chosen gate-oxide materials. So we will do that. Moving on. So this is the methodology, how we have done the work. You can see at the left side, a device structure of 3nm gate-all-around FET is shown, which is simulated. In the middle, this is the cross-sectional representation of the structure, and at the right, the parameters table is shown, which are used to simulate the device. Moving on, simulation results and discussion. So you can see this is the IDVG characteristics for different gate oxide materials. You can see from the graph the drain current increases as the dielectric constant increases. The slope here for the titanium oxide is the highest. Titanium oxide has the highest peak also here, as well as the threshold voltage for titanium oxide is also the highest. As the drain current increases, the on resistance reduces here. Moving on, this is the IDVD characteristics for different gate oxide materials. Here you can also see the drain current increases for the titanium oxide before the saturation. As the drain current increases, the on resistance reduces here. Transconductance GM will increase here as well. The oxide capacitance decreases here. From the equation we can find out that as the drain current increases, the oxide capacitance decreases. Moving on. So this is the IDVG characteristic in logarithmic scale for different gate oxide materials. You can see the drain current increases exponentially below the threshold voltage here. When the voltage is applied 0.7 volt, the current stabilizes for all of the materials here. Moving on. So this is the transconductance versus gate voltage graph for different gate oxide materials. You can see transconductance increases with the increment of the dielectric constant. So highest amplification rate for titanium oxide is gotten here as the transconductance rate is the highest, where the lowest amplification rate is gotten for silicon dioxide as the transconductance for silicon dioxide is the lowest. Moving on. So this is the performance parameters table for different gate oxide materials. If you notice the last row of the table, the titanium oxide is giving us the highest on current, the lowest off current or the leakage current. The highest I on or the on and off current ratio is the highest for titanium oxide, and the subthreshold slope, subthreshold swing, which is a short channel effect, is the lowest for titanium oxide. On the other hand, we are getting the highest on current, the lowest on current for silicon dioxide, the highest off current or the leakage current for silicon dioxide. Here the I on I off ratio is the lowest, and the subthreshold swing here is the highest, which is a short channel effect. Moving on, this is the conclusion. So the effects of variation in on and off current ratio, subthreshold slope or swing for 3 nanometer cylindrical shaped GAAFET are obtained using Silvaco TCAD in this work. The oxide materials having high K dielectric constants have higher on current, lower off current, higher on and off current ratio, and the lower subthreshold slope. So titanium oxide is found better than the other materials in case of lower leakage power, as the leakage current is the lowest, higher amplification rate as the transconductance rate is the highest, higher switching speed as the ion and I off ratio is the highest, and higher gate control ability as the drain current increases. To overcome short channel effects, the titanium oxide performs better. We noticed from the table that the subthreshold slope for titanium oxide is the lowest. Further goal is to find a cheaper material with a better performance of this study. Till now, hafnium oxide can be a choice considering the cost. So these are the references for the study. So that was all about the presentation. Thank you.